All right. So today it is my hope that we can wrap up 8.2. I think we're done at 8.3. We can almost finish. One last thing.
Ooh,
I thought I could take this opportunity to show off some funny-looking kids' schoolwork. How many of you remember me telling you that you should make a cardboard mock-up before you get going? This is a spectacular mock-up. Here's what this lets you do. You can measure your angles to make sure that they satisfy your plans. You can look at the logistics of where the doors need to go and how big to make them, how best to articulate the things that you need to articulate. Is that going to be a challenge? Maybe we need to move the location of our door. It lets you measure the size of your panels and strategize what goes on first and second. And is it safe to assume that you could do this in one afternoon?
Yeah.
So I don't know if I'm qualified to out the makers of this house, but I'm sure you can follow the gossip chain and figure that out on your own. I think this would be very helpful as a single afternoon investment on the way to building the final model later on. I'm excited to see this house. Does period 5 have any 2 student groups? Group of 2?
Oh, yeah.
Okay. You 2 are a group of 2?
Yeah.
Would you prefer to stay a group of 2, or would you like a third?
Yeah, I mean, it'd be helpful. Yeah.
Yeah.
What?
Yeah.
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 Matt, who's in yours?
Taylor, but Gavin isn't here anymore. So Gavin was in our group, but now he's not.
Gavin switched peers, or he left? No, he left class. Yeah. Taylor Robbins?
Yeah.
He's in my P4, right?
Yeah.
Rafaela, Carter, Matt, I'm going to throw it out there to a kid in period 1 who's been stranded solo to join either of your groups.
Who is it?
I don't know if I should say yet, because if he chooses Matt over you, I wouldn't want any hard feelings. I guess you'll find out eventually. Angel, I think his last name is Escobar. I forget his last name.
Yeah, it's like,
No, it's not right
Yeah, Escobar. That's a famous last name, isn't it? It's that Escobar. All right. Let's confirm that we're done with 8.2. I think we're done with 8.2. Please take out your 8.2 and we'll make sure that all those study goals are done. Is that a study goal? Is that a study goal? Were you here yesterday? What's up, good kid? Here we go. Too many noises, please, not me.
Cookie and milk. Bye? No? Okay.
Number 10, the Keeling curve, the CO2, seasonal breathing, ups and downs, different hemispheres, ocean, land. Good? Number 11, ice cores, limnopaleobotany, which is upon the bottom of lakes. The stuff you get underneath the ice caps. Good. Number 12, climate versus weather, my crummy sports analogy. Number 13, you copied it out of the book, nitrogen, oxygen, argon, or whatever. Number 14, the atmosphere is like Jawbreaker, and there's ozone here, and there's different temperatures, and the source is DES. Number 15, there used to be something here until this morning. And then we had a single convection cell that we demonstrated yesterday with red and blue. And then we talked about how that all spins on the planet. We're going to come back to how that all spins on the planet. Number 16, what makes our Earth warm?
Sunlight traveling to the ground and the ground
energy being absorbed by objects on Earth.
See, if you say it fast, you just say the sun. But if you say it slow, like the light being absorbed, and that gives energy transmitted heat. Number 17, Milankovic, the wackiest Serbian. And number 18, albedo is reflectivity, like shininess, like ice and glossy plants in the ocean surface. I believe we are done with assignment 8.2. Is that correct? Yes. Please stash that and go to 8.3. Oh, greenhouse effect. We talked a lot about climate change and stuff for days and days. But we left out the greenhouse gases and the anthropogenic greenhouse gases and their sources and rates of change and relative contributions. That's up here. Then we'll do number 21. We already did 22. I'll list off number 23. We'll do number 24 and hopefully get right up until the end. Maybe not quite at the end of 8.3 today. Everybody pepper Josie with text messages to get a copy of that photo. Take a second. Take a second and write this down, but please look at me. Leave some space over here. Take all this, leave some space over here. Ready, set, go. Go. That's numbers 19 and 20. See? $19 and $20. If you were to take like a minute and a half, 2 minutes, scribble as quickly as possible, I'll fill in. Ready, set, go. Yes.
Biggest one of the year.
Gotta go.
mostly there? Here goes. If I say it and you didn't already know it, write it down. Most of what you copied is like the outline of what I would copy if I was a student. Some of this you should already know and it's obvious. For example, please look up. Y'all know that's water? Don't need to write that. Y'all know that's carbon dioxide? Cool. Y'all know that's methane? That's nice. Be careful. Very important detail. This is like one of those things that students get wrong in this unit. N2O is only in study goals 19 and 20. For the next week, we're going to talk about nitrogen oxides, which are called NOx, like NO, NO2, NO3, and maybe even NO4. Those are not the same thing. So I'm trying to warn you to prevent confusion later down the road that this is just a blip in the unit. It will only show up a couple times, 19 and 20, right here, then it's over. Yeah?
Alright, so NOx is nitrogen oxides, N2O is...
I don't know if I'm saying it right. I think it's called nitrous oxide. Anybody speak chemistry?
Wouldn't it?
Yeah, nitrous oxide.
See?
I'm not confident in my nomenclature anymore.
Nor am I. I don't talk about that one a lot, so I just call it N2O. I can tell you it's laughing gas. I'm fairly confident that's the one that you inhale when you get your wisdom teeth pulled. Anybody want to Google this so we can just settle it and I'm not guessing incorrectly? Thanks, nitrous oxide. N2O?
Yeah, commonly known as laughing gas of nitrous. It's a chemical compound, an oxide of nitrogen with the formula N2O.
Bingo, alright. So, the laughing gas, N2O, nitrous oxide, is different from the NOx. Nitrogen oxides are a different thing.
Are you drunk?
Next.
Are you trying to search stuff?
Please look up. Here's another source of confusion. Major source of confusion. Ozone is ozone anywhere you make it, but the greenhouse only applies to tropospheric ozone. This is a big source of confusion. Ozone depletion, the hole in the ozone layer, the fact we don't have enough ozone, we get too much sunburn, skin cancer, yada. That's stratospheric. That's a different layer. So far, we're not doing any content up there. Josie, I'll tell you later, I promise. At this point in the course, we're down here. Troposphere, near Earth atmosphere. The lower atmosphere. So I'm discussing ozone as a tropospheric gas, where it's a problem. Not in the stratosphere, where we need more of it. You ever heard the thing, I wish I could get fat in a different part of my body? Yeah. It's my problem.
Where would you want that?
I'll show you later. This is fat in the wrong part of your body. We need more ozone up in the stratosphere, just not down here where we live. That's not good for us. And finally, please look up, because this is another very, very challenging thing in my class, and I don't think I have time to teach you enough, and I don't know enough, and I could just start babbling at you, but we're just going to try to keep it succinct. Please look up. There are many industrial gases that cause climate change. CFCs, other chlorinated gases, halons or halocarbons, sulfur hexafluoride, SF6. These are industrial greenhouse gases. Stuff that we use in a factory to do stuff. So far I just did one column so you would know what's on the left. Anybody want to ask me anything in just that column? No? Next. If you look at the total greenhouse effect, it's mostly water and CO2 with a little bit of this other stuff. I gotta warn you, you probably shouldn't memorize those numbers, because I made some pretty dramatic estimations. Technically, different seasons, different parts of the atmosphere, you get really different amounts of water, CO2, and others. I know that this stinks, but at different times in different places, those percentages shift a lot, a whole lot. So here, you can put a gigantic note that says roughly on average. Like, just looking at that, it's making me uncomfortable. I don't think it's right. I want to make that a 10, a 3, and a 2. But you can tell I'm just kind of shooting from the hip, right? Like, different parts of the atmosphere, different times, different seasons, it really does vary dramatically. Water can be as little as 30% of greenhouse effect, and it can be as much as 70% of greenhouse effect. Over land versus over ocean, in the sun versus in the shade, in the, at nighttime versus the daytime. But here's where things get interesting. This is how much we've added over natural levels. So, starting with 100% natural, humans have added on to that another 42% of CO2 today. We started with 280 parts per million before industrialization. Humans have added 42% of that to that original value. We're up to about 400 now. We've, added almost half again. Please look up. We've more than doubled methane in the atmosphere. That's significant. That's very significant. We've added a little bit of nitrous oxide, and I'm not really confident that this is very avoidable.
Why is there plus minus next to it?
Because I'm hesitant to call it a single number, because that's really shifty, difficult to measure. And there's a lot of debate about which methane we should count. So, are we responsible for the methane that's bubbling out of the ocean because of changes in currents? Would those currents have changed anyway? Is it El Nino that's causing more methane hydrate to leave on the continental shelf of Chile, or is that humans?
So it's just like more or less.
So this is the rise in methane since pre-industrial times. It's just not clear that humans are entirely responsible for that rise in methane. So that says more or less 160%. That's a pretty safe medium. Some people say more than 160. Some people say less than 160 rise because of humans. Please look up. We've probably added all of the ozone in the lower atmosphere, but it's important to point out that ozone in the lower atmosphere is kind of complicated because it moves and reacts naturally. And please look up, the industrial gases are entirely man-made. We make all of them. None of that is natural. They did not exist before humans made chemistry. These are not chemicals that are possible in nature. They're called industrial because they're basically synthetic. They're man-made gases. Anybody want to ask me anything before I move columns? I need to make an analogy. Maybe it's a metaphor. I forget which one is which. I need to make an analogy. I'm gonna make an analogy. Yeah, I need to make an analogy that I think might be a touchy subject. So.
Your feet on the ground is like the worst thing I've ever heard in my entire life. Yeah,
It's the shoes.
yeah, that really.
Slow inch
Okay.
I feel like you should
I walk around in the mud in the mornings and then I drop dirt all day. This is the worst floor in the entire school. Okay. Here's my metaphor.
What was an analogy?
Stop it! Y'all mix those up or is it just me?
We need to go back to Forrester's class.
Anybody want to settle this real quick?
It's an extended analogy.
We need to hear it first.
An analogy is an extended metaphor? I'm going to stick with analogy then. Here we go.
Oh boy.
Here we go.
Simile, probably.
Like
It's an illusion.
I do know what those mean.
Flipping with gas.
Okay.
Just say it.
Parallel structure.
You know that you're going to have a bunch of students in a room, and maybe many of them are quiet. If you have a bunch of average noisy ones, that creates like an average volume in the class. And if you have 2 or 3 really noisy ones, that can really elevate the volume of the room. Agreed? You can see why this is a touchy analogy, right? You might be able to say that most of the students add no noise. Average noisiness brings the levels up, and then a couple of individuals can really add a lot of noise. Is that a fair statement? So, in our atmosphere, most gases are not greenhouse gases. CO2 traps a little bit of heat. Methane traps 10 times the heat. And these trap as much as 23,000 times the heat. CO2. Let me clarify and then I'll get to your question. One molecule of these holds and releases 23,000 times the temperature of a molecule of this. You could have 23,000 CO2 molecules, and that would equal the heat storage and radiation of a single SF6. In other words, these are really generally kind of quiet. It takes a bunch of atmosphere of CO2s to cause some warming. But it takes just a few of these. They're almost impossible to find in our atmosphere. But just a few of them are responsible for a tremendous amount of extra heat. Because they're so powerful, like a loud kid in a room. Question?
How come it says that they contribute to none of the total greenhouse effect?
Because most of the greenhouse effect is H2O, and anyway, I didn't want it to be 0. I wanted it to be a very negligible small number. But when I was rounding, I just put, remember that these are kind of wishy-washy, me rounding at the last minute. So it's a small percentage. Because, actually, one thing that I have to really clear up here, that do you realize that our greenhouse effect is extremely powerful? In the dark side of the planet, it should be negative 250 degrees or something. Like, the natural greenhouse effect takes us from Martian temperature variation up to pretty cozy room temperature that you and I evolved in, and that's all pretty nice. And the extra bits of greenhouse gases are warming us up by like a degree. that's very significant and is very serious and all. But there's a lot of greenhouse effect. We're just adding one blanket on a big pile of blankets. So of that, this doesn't really become very significant, but it is a big part of what we've added. Does that answer your question? Yes.
Is it just because of the size and like complexity of the molecules that they?
Bond geometry.
Yeah.
Yeah, I don't know how to clarify. They wobble really hard. So you can they can put a lot of heat in there and they wobble like crazy. Fluorine bonds, if I'm not mistaken, are extremely strong, and that has a bunch of them because it's an SF6.
Are CFCs still being used today, even though they've been banned in countries?
They are still being used kind of willy-nilly in some economies that didn't participate in the 1980s treaty about ozone safety. And they're still being used in very rare cases, even within those countries, where there are some exempted applications.
Do you know what the ratio is from CFCs to CO2 molecules or no?
CFCs break down in the atmosphere too.
Oh, okay.
So a lot of the ones that were put up in the 80s are gone now.
Yeah, I thought they already did their damage, sort of.
Anybody else? Okay. Now, there's a column missing on the right. So I'm going to talk about this one and the missing column together. I think Ashlyn asked me about what is naturally the total greenhouse effect, which is everything that we experience today. And I said, remember that there's a bunch of natural plus humans have added a little bit, right? Here's what we've added. That's this one. What we've added is no water. About half of the anthropogenic effect, the human warming, about half of that is CO2. And this is the part where you've got to have a column on the side that I didn't have space for on the whiteboard. Our CO2 comes from all the things we light on fire. Wood, coal, trash, I suppose. I guess, but let's focus on the fossil fuels like methane, natural gas.
Wait till the next one is what we burn.
Is where it comes from. So CO2 is from burning things. And you know, CO2 is basically tied to everything in your modern universe. Like when I say CO2, everybody thinks about cars. But cars is kind of chump change. A lot of CO2 comes from the airplanes or from the tanker ships and trains and buses that we don't think about. But a lot of CO2 comes from electricity. And a lot of CO2 comes from home heating and cooking. And a lot of CO2 comes from burning wood, which you and I don't really do, but is still the planet's #1 energy source. Charlie, put your phone away. And we've basically got CO2 tied to everything. Like your stupid cell phones. Think about it. Like you go on Snapchat and there's like a Snapchat server somewhere. I don't know where they have like the Snapchat servers. Those are all running on electricity that runs on fossil fuels that make CO2. Your phone was mined using CO2 producing energy sources. Built in a factory that gets the energy from fossil fuels. The work was done by people who each have a CO2 footprint. And basically, here's my point. This comes from burning stuff like fossil fuels, etc. But it's tied to every human activity. Anything that you like. If you like it, it probably gives off CO2 somehow.
Going on a walk on the beach.
Okay, except for that. And snuggling. Yes?
Is the reason why CO2 is so much more than everything else just because we convert everything else into CO2?
I guess it's because our entire world runs on carbon bonds.
Yeah. But like we burn methane into CO2, so is that why it would make sense that CO2 is so much more than methane and all the others?
Yeah, I mean, you mean how we off-gas methane and we burn that to make
Yeah.
CO2 and we can't bottle it? Yes, but that's not even, if you add that across the entire planet, that's not even one of those 50%. My point is, anywhere you look, you're making CO2. Like, our entire existence makes CO2. I don't know how to say this differently, because like, I used to say it's fossil fuels, and then kids would get really focused on the fossil fuels, and they forget that it's all the other stuff that's remotely based on fossil fuels and tied to our land use practices, and like, you cut down trees and that's more CO2, and like, CO2 is like modern life. But if you want to be explicit, the primary cause is the direct combustion of fossil fuels. Okay? Next, methane is the next biggest chunk of humanity's blanket. And methane is anaerobic decomposition. You probably know this by now. I've said it a lot this year. Decomposition, like breaking apart bonds. Anaerobic, like no oxygen around. So methane comes from any place we have anaerobic decomposition. Humans are responsible for landfills. We're responsible for rice paddies. We're responsible for wastewater treatment. And we're responsible for a lot of livestock that farts. When I saw this, I didn't believe it, so I've been looking and looking and looking and looking, and I'm still pretty sure it's right. And if you want to prove me wrong, I'll hear you out. Anthropogenic heating. CO2, methane, industrial gases, ozone, nitrous oxide. Check this out. Cars, livestock farts. You get more global warming from methane and livestock farts than you do CO2 contribution to warming from cars. Cars make a lot of CO2, but CO2 doesn't add a lot of heat. Cows and pigs fart a lot, and that methane is 10 times more powerful than CO2. So we as a species cause more global warming by force feeding livestock stuff they can't digest. You know, you want them to grow fast. So you just feed them grains, and they're just like, oh God, I just don't know if I, oh God. And the cows and the pigs fart so much that they cause more warming than all the cars. And this is what I mean. Everybody's like, oh, I got this new car that has like a 3% better gas mileage. I'm an environmental hero eating a cheeseburger. And I always feel like, you know, you're still making a ton of CO2 with that car. It's just a little marginal decline, but you could have made a huge difference if you had just cut it out on the livestock.
The problem is, if I stop eating, it's not.
Say what?
The problem is, if I stop eating a hamburger, it's not going to do anything.
Well, it's like saying if you stop driving, that's not going to make a difference either. Like, all we're doing is measuring your personal options. And as a personal role, you make a bigger difference with your diet than you do with your car. By the way, this assumes that you're an average human. Yeah?
Do animals create air pollution too?
Other than these, because methane is an air pollutant.
Well, other than
Probably, like some particulates. When they walk, they must trample some dust into the air. I would assume that, like any of us, there's other stuff in the farts. They smell bad. Does that count? I don't know, probably. But the big one that we really do need to put on the board because it scales up to be a global problem is the net volume of farts from livestock is really significant. Plus, let's remember that in the slaughterhouse, there's anaerobic decomposition in the tanks of offal or whatever. Like, it really adds up. Yeah?
Are you just saying livestock? Like, are there like fish involved in that or no?
No, I mean intensively farmed livestock. So coincidentally, if those cows ate grass, they would digest it better, grow more slowly, and fart less. So really, it's how we force our livestock to eat that makes them fart too much.
But if us not eating like a hamburger or whatever, they're still being fed it. So like.
Well, that's the same thing. If you lower demand, the next guy is going to buy less cow to feed them less. Just like cars. Like if I don't buy a car, someone else is going to buy it.
No, but like it's already being produced. Like the car hasn't been driven.
Same thing. Like the cow hasn't been eaten if you don't eat it, so it goes to waste. The supermarket buys less next year. Just like the car dealership sells less cars next time they order them. I don't know. Yeah.
Alright, sorry, another question. Is grass-fed beef any better or not really?
They fart a lot less. Okay, please look up.
Sure.
Nitrous oxide is from agriculture, farming. It's not a lot of our blanket, and basically all farming uses nitrogen fertilizers, so it's tough to fix that. Ozone comes from electromagnetic fields, basically high intensity electronics. Have any of you ever smelled a lightning storm? You know that smell?
I know what you're talking about.
Okay, that smell, you get that when you go into the computer labs, especially the one in the 30s, which has older computers and bigger screens. That's bad for you. That's ozone. Lightning makes ozone, and so do electromagnetic fields. People who work in server farms or whatever, they have to use like really, really fancy air filtration. One of my students in period 3 told me that her mom's company had to move all the computers and reroute all of their stuff because they realized that everybody was getting ozone poisoning in their office building and they were all getting crazy headaches. They had like a plague of migraines as the company grew.
What does ozone poisoning do?
I don't know, apparently gives you migraine headaches. Okay, oh, well, it is an oxidant. You ever heard of antioxidants?
Yeah.
Like the thing you're supposed to eat because it's good for you? This is an oxidant.
So the opposite.
So bad for you.
Yeah, because it's got an extra oxygen atom, so whatever that is, I don't know. I ain't no doctor. You would be surprised to hear this. I have no medical training. The industrial gases, though, here's something you got to put in your notes somehow. Very, very rare, very, very big part of our blanket. It takes small volumes to do a lot of heating. And these are generally kind of obscure industries. Like spray paint and hairspray were the main source of CFCs for a long time. Like Freon was the main source of SF6, like industrial coolants.
What's the little thing we like sprayed on the dust and the dust like goes away?
I believe that would, no, that's just pressurized air.
Oh.
Yeah, it's just pressure.
I think it's pressurized air. So like clean out a keyboard?
Yeah, and it's like really cold. Like, if you spray it on yourself, it like gets all
I
crazy.
think it's just pressurized gas. If it's not pressurized atmospheric, it's pressurized gas. I'm not smart enough. Somebody else raise their hand? Yeah.
Sorry. You said it takes a little to do, like it uses a lot, whatever, but it only takes a, what did you say?
That it takes just a small volume of these gases to cause a lot of heating. Now, the reason that I mentioned this, please look up, it's pretty tough to convince the world to stop having a better quality of life. Like honestly, we always talk about CO2, and there's a reason it's been difficult to lower CO2. Because even if you want to be a hero and stop driving a car or stop using electricity, the world's poor are all trying to claw their way out of pretty challenging lives, and almost every improvement in the quality of life for the planet is more CO2 production. Like, go ahead, be a hero. Somewhere there's a mother or father who wants natural gas to keep their kids from freezing at night. Like, go ahead and be a hero. Somebody wants their food to stop spoiling, so when they can, they're going to add a refrigerator. CO2 is tied to such fundamental things that it's pretty tough. We should all diet on the CO2. Yes, I'm not saying that's pointless. I'm saying that CO2 is tied to quality of life, and the planet is trying to have a better quality of life. There's billions of humans who will grow their CO2 footprint. And that's probably fair for them. However, these are little things. You make a can of spray paint cost 20 cents more and you can fix that. How many of you are deeply invested in 20-cent price difference in a can of spray painting? You make industrial coolants a little harder to dispose of. How many of you would be bothered by that? We gotta try a little harder to make our microchips in an airtight factory. So my point is, these are the low-hanging fruit. Like, this is really fixable. We could take a big slice out of man-made global warming with some really minimal industrial changes. I'm done with number 19 and I'm done with number 20. Questions for me? It is, yeah.
Where does N2O come from again?
Soil chemistry. So remember the nitrogen cycle? Nitrogen fixation, ammonification, denitrification, nitrification, that stuff?
Yeah.
As chunk change of all that soil ecology with bacteria, there's a little laughing gas coming out of the ground.
Okay.
And the more ammonium you add, the more laughing gas comes out of the ground. But we really can't grow food without adding ammonium. And any way you do that, synthetic or organic or slow or fast or high tillage or low tillage, you're pretty much going to get some nitrous oxide. We could make some improvements, but as long as we're feeding humanity, that number won't shrink too much. That's basically proportional to people eating. Anybody else? Josie, I think I need to give you a haircut, bro. Yeah. Okay. Got a paper cutter.
Can you do
Yeah.
Okay.
Number 21 is fast. 21 is fast. How many of you have heard of coral bleaching? Cool. For anybody who hasn't, I'll go really fast. Coral is a symbiotic animal that has an internal skeleton. The fleshy coral bag is outside its skeleton, and that fleshy bag houses symbiotic algae. Coral are filter feeders, so they take algae from the ocean and they keep them in the bag. Okay. Having a photosynthetic organism inside of that bag is helpful to the coral. I don't really understand the chemistry. Now, when the coral gets shocked and life is hard for the coral, they go and they squeeze all the algae out, making them appear bleached. Because when the green is gone, you can see the white skeleton inside the animal. My old friend Bob Trench at UCS Brodog was one of the world's leading authors on coral bleaching. He's dived coral reefs all over the planet. He was one of the first guys. Back like in the 1970s, he was already diving and writing about coral. He started as an ecologist and started paying more and more attention to the bleaching. He had a distinguished 30-year career writing academic articles about corals and bleaching. And they thought that it was water pollution. Then they were like, hey, maybe it's this climate change thing. So they thought it was ocean temperatures. And right before he retired, he worked with a bunch of other nerds at UCSB to write a different article. Do y'all remember what happens when you mix oxides and water? You get acids. Acid mine drainage, we talked about this in the previous unit. Now, you all realize that 78% of our planet is covered in water, and we've just added a bunch of CO2 to the air, so you understand what we've added to the water? Please look up a bunch of carbonic acid. Here's the wacky thing about life in the ocean. Temperatures change all the time. Think about it. When you go into the beach in Santa Barbara, you ever notice that it's really cold sometimes and really hot sometimes? Santa Barbara's not the most dynamic part of the world's ocean. We go from low 50s to low 80s here. So ocean life has big temperature tolerance. Please look up. A normal oyster can tolerate water with about a 50-degree temperature range. And they're happy anywhere inside a 10-degree temperature range. But they're pH sensitive down to 3 decibels. Because the ocean is a gigantic body of water. I made up this number. It was just to show you what I meant by 3 decibels. That's not the pH of the ocean. I made that up. It's not accurate. Because the ocean is a huge body of water, its chemistry doesn't change very much. Over evolutionary time frames, the ocean's pH has been almost the exact same. And recently, the amount of CO2 that we've put into the air is enough to change the ocean's pH by about the 2nd decibel. In other words, sure, we're heating the ocean, and yes, that does cause issues, but acidifying the ocean turns out to be a much bigger issue for ocean ecology. Anybody want to ask me something about 21? Reaction for ocean chemistry? Cool. Number 22, I think we already talked about, correct? Climate models. You guys got to rally. We still have like 20 minutes. We still have 40 minutes. It's brutal, I know. I warned you at the beginning of the unit. We got nothing but lecture in this one. I know it's a marathon, but you can do this. Everybody's bonking. I can see all of you just like.
It's about 10-minute nap time.
You got to do like me.
Handlebar stuff.
Triple dose coffee.
Handlebar stuff.
Wow. It's like the best.
Crush cakes is better.
Stop.
I'm not a big fan.
Crush cakes?
Crush cakes or handlebar?
I said handlebar. I meant handlebar, but I like crush cakes. I like free crush cakes.
Have you
Yeah,
tried
I
Handlebar's
got
chocolate
it.
croissants? Oh,
Yeah, their croissants, their food is really
Nah,
good. The pastries
so
are.
good.
And they're hot chocolates.
Their drink,
See?
pretty much all of their drinks
Are just not my favorite.
Kind of
I got it. I got it figured out. When the class starts to bonk,
We need a
I'll
lot
just
there.
say food, and everybody goes, "Oh yeah, food!" And then we get back to class, and everybody's all bright-eyed and bushy-tailed. Hey, check this out.
That's from like.
That's actually real. Is that from like a long time ago, or did you buy it?
you're not gonna eat that. It's like one every day.
No.
Are they still?
I can't eat a lot of candy.
We're not gonna eat like 3 of those in one day.
You do.
I had 4 donuts.
everybody's coming to life. This is good.
Not as good as you, Toby.
Stop trying to kill me, I'm not your fault.
Take that.
You too.
Is that a thing that everybody trips from?
Yeah.
Everyone can say everything to Rel. It's so hard.
Wait, do people not trip?
Was it, what's the state thing? You have 2 stickers there. What's the
We're all
state?
different.
It's mine. Hold on, just come.
What is it?
I've got a lot of stickers.
What is it?
Like clothing or whatever.
What about your sticker on the back?
Clothing and stickers.
Why is it under?
My other kids. All right. Thank you for working through that. I've got 2 study goals left to lecture, 23 and 24. And then we'll call it a day. Because we already did number 22 about circulation models, and we already did number 25. When Devin was absent, we talked about the conveyor belt. So all I have is 23 and 24. And 23, I'm just going to rattle them off really fast. So you can just write it down and then move on. No, that was the
Oh, it's okay.
Good. Here we go. Can I have an example of positive feedback, please?
Apples
Cocaine.
ripening. Fruits ripening.
Something about your wife being mad or something. You're giving birth.
It's actually true.
That's what
That's
I said.
true. The contractions cause
That
like.
applies to one gender.
There was some lady afraid to like came out of the ocean with a baby. She was just like swimming.
Stop.
Fruits ripening is an easy one.
I'm not.
Why are you so shocked?
As is.
None of these make any sense.
Fruits
How
ripening.
is
Cocaine
is
addiction makes sense.
Yeah.
yeah? Cocaine addiction makes sense.
Kidneys don't
Fruits
have
ripening
cats.
doesn't make any sense, does it?
No.
How does the output?
Jesus. That was terrible.
When a fruit ripens, it releases a chemical that makes the fruit around it ripen.
Oh, fine.
It releases
Okay.
a chemical which
Yeah.
makes the
All right.
fruit
Isn't it just
All right.
Nice, sorry.
Yeah, all right. Fine.
No.
Back to me. I liked it when you were more sleepy. I don't get the childbirth one, but maybe later you can tell me. Some people say cocaine addiction, positive feedback because it makes you feel good, so you use more cocaine, so it makes you feel good, so you use more cocaine, so it makes you feel good, so you use more cocaine. I get it. That's a positive feedback. The point is not that it's a good idea. It's not like positive life decisions. It's like where the output causes more of the same cycle. I regret telling you to think about food. Please think about hunger and napping. Yawn. See, now everybody talks to yawn and then you're going to go to sleep. It's so easy. Okay.
It's a positive feedback.
It is. It is. Because as soon as you say yawn, more people yawn, and seeing each other yawn makes people yawn more.
I thought it was just
The
yawning.
sound of yawning, the sight of yawning, the word yawn. Now, so,
Mythbusters did a thing.
a negative
Yawning.
feedback. Excuse me. I do need to finish these today, please. A negative feedback is a system whose output gives you less, like self-regulating. And there's been a lot of question. A lot of people say, oh, well, the planet heats up, and then this thing's going to happen, and climate change will go down. Because, you know, it's like a balanced equilibrium, and Mother Nature is in charge. And I'm sure that, you know, it's going to heat up, and that'll somehow make things cool off. So people have suggested positive feedbacks that'll accelerate heating. People have suggested negative feedbacks that will slow down global warming on its own. And I have a list of these, and it's study goal number 23. Negative first. Number 1. Algae grows better when it's hot, and they'll soak up the CO2. Number 2. CO2 makes plants grow, and plants are shiny. So plants will raise albedo. And that'll somehow lower temperature. Because, you know, plants are shiny. More CO2, more plant area. More plant area is less heat made by the planet. Negative feedback number 3. Maybe all that extra water vapor will make more snow and ice in cold places. Raising land's albedo again. Increased ice and snowpack. And number 4, here comes a key detail that was complicated earlier, so get ready for the detail. More water vapor could mean more, double underline bold circle, high clouds. If all that extra water vapor makes high clouds, well, those are going to be icy. And ice is shiny.
Albedo.
Albedo. Yo.
Mr. Forster mentioned something about like putting a bunch of like metal flakes in the air
Yeah.
to reflect stuff. Is that plausible?
Yes, it's plausible.
Yes.
Yes.
Would it work?
Nope.
What if we're like all bald and just tiny parts of
No, I was like, listen to it.
Here's what we do.
Email it to me. Email it to me. Yeah. What?
Listen to it.
No, it's okay.
No. Ellie.
I just said, what if we were all bald? Just the shiny part on our head. Just raise albedo. Everyone on the earth.
So the question is, how much albedo would we need? For example, people have done some interesting projects. Check this one out. Check this one out. I'm trying to go forward. You're just holding me back.
Oh my.
You take the 10 biggest cities, paint all the roofs and paint all the roads white.
Ooh.
Cancel out 1 year of global warming. Because albedo, that's how much it would take. The math exists. It's known.
Wouldn't your house be really cold though?
Not very cold.
What
Yeah.
if we just paint New Mexico white?
Sounds like a good plan.
Yeah.
You want to make Mexico white again?
New Mexico. Like, you know how they like say like cover it in. No.
Get back to me, please.
No.
I need to move forward. This isn't working for me. I think I would need everyone to be quiet all the way to the end just to keep up with the other periods. Then there's the positive feedbacks. What if that extra water vapor makes low clouds? Underline, circle, bold. Low clouds are, please look up, the main greenhouse gas. That would be positive feedback, right? Planet gets hotter, there's more water vapor. If those are low clouds, we trap more heat. At the beginning, there was a movie where the guy said, we're not really sure whether the extra clouds will be high clouds or low clouds. I think the movie was backward. This is now settled. High clouds raise albedo, lower the temperature, negative feedback. Low clouds are steamy, water vapor, greenhouse gas, raise temperature, positive feedback. Yeah, Ava?
What atmosphere are the high clouds in?
So bottom of the troposphere or top of the troposphere. We're still all parts of the troposphere.
Okay.
Next, you all know the biggest positive feedback. I told you about it in the energy unit. It is
It's carbon, right? Or
positive feedbacks in the permafrost. Methane hydrate. That's right. As the planet heats up, the permafrost melts. Permafrost melts, more methane goes up. Makes the planet hotter, more permafrost melts. the biggest positive feedback, the really scary one, is methane from melting permafrost makes the planet hotter, more melted.
Bye.
Hi.
Goodbye.
So there's one that I think is totally hilarious, and apparently it's very real. People in like the modern world, if you can, on a really hot day, you go inside and you turn on the AC, which runs on electricity that's usually supplied by fossil fuels that give off more CO2, which is actually a global positive feedback now. Because so many people have access to air conditioning, we're all going inside and cranking up the global warming.
That's ironic.
You gotta admit that's pretty hilarious, right? Yeah.
Solar powered AC, everybody turns the AC on.
I know.
That could, yeah.
But we use the AC and albedo. Nice.
Yeah, because the solar panels raise the albedo.
Exactly.
I see you've been reading for
Chill, no, don't do it. Last positive feedback is not in your book. It's called roses, which are rain on snow events. Rain on snow events. Chris Jonas just showed me the forecast for Tahoe. They're expecting snow every day for like 10 days or something. Snow on snow on snow on snow just makes snow pile up more. But if you just raise the temperature of a snowy climate, you'll get more rain on snow. And rain on snow makes it melt. I got busted. I used to use my skateboard to get around on campus, and the principal pulled me in with all the assistant principals and was like, "No, it's yes."
What if you considered skateboards?
Right at the beginning of Beckio.
You're causing these problems.
You should do it at the end.
Next year, I'm back. Okay. Rain on snow events. I just announced that to the YouTube.
Use a
world.
scooter.
No one's watching.
Men don't use scooters. Okay.
That's my
Rain on snow events. Rain on snow events lower the amount of snow and ice on the surface. They lower the Earth's albedo, exposing rocks. And you all realize that everything I've just mentioned is something we can add to our models, right? Remember I told you we have models that have albedo now factored in? So for example, if you can model temperature, rain, where the snow is, where there's rocks underneath the snow, all of the major models show that the negative feedbacks are really, really subtle. Like how much CO2, how much temperature helps how much algae, helps how much forest, makes how much. Like all the negative feedbacks are really pretty subtle, but the positive feedbacks are very, very powerful. The methane hydrate thing is a really, really positive feedback if we can melt all the permafrost. The rain on snow events are really powerful. That's the main reason that Greenland is melting, is because of how many rainy days there are per year on Greenland. And so in the modeling of these, you've got global warming, negative feedback's pulling it down a little bit, positive feedback's driving it up a lot, which is why even if humans disappear, the planet keeps heating. Because a lot of these positive feedbacks are snowball effects that we've already started tumbling down the hill. Yeah?
For the rain on snow thing, so when it melts, and then like let's say the next day it gets below freezing, wouldn't that turn into ice and then have the albedo effect or whatever?
True, but you've lost area of snow every time you have a rain on snow event. So if you're on a mountain, right, like you good amount of, and imagine you've got some like spring conditions. You might be able to like see snow on the mountain. If it rains that night, next day you'll have a little stream of ice, but you've exposed a lot of rock and gravel, right?
Yeah.
Where the snow was thin, and the rain kind of poured it downhill as water. So you're right that ice has good albedo, but so did the snow in the first place. The albedo of snow and ice is almost precisely the same because you realize that snow's a little piece of ice, right?
Yeah.
So lowering the land area of snowpack is the big impact of rain on snow. That's the big deal with green. Okay, one study goal left. I think we might be able to, don't get carried away, but I think we might make it. I'd like to talk about study goal number 24, El Nino. And man, I don't know why, but the environmental science test likes to call it ENSO, the El Nino Southerly Oscillation, which is super obnoxious because the entire world calls it El Nino. ENSO is the most random, bookish, like super academic, nobody knows what you're talking about, unnecessary contrivance. I hurt my hands. Please look up. I'm hoping that everybody remembers. We had the convection cells in the atmosphere. We spun the Earth underneath those convection cells. And watch me, it's going to be necessary later. That makes a gyre here and an opposite gyre just below it. Remember those? They're still on the board from the time we did that drawing. Atlantic has them. There's one in the Indian Ocean that I've erased already. And you might be able to see that there's matching ones in the Pacific. BT dubs, this is why there are the so-called trash islands, which are kind of a lie. But anyway, aggregations of trash inside these.
Wait, why is it a lie?
Because everybody visualizes something which is false. When I say trash island,
Oh my God.
I'm assuming that if you're an average human being, you have a vision of like solid trash floating in the ocean, or at least something that you would be able to see from a sailboat. And it turns out that trash islands are not like that at all. The photos that were trafficked in many conversations about this topic are usually from bays or river mouths where a bunch of trash aggregates and makes visible floating rafts of garbage. Plastic pollution in the ocean is a real serious big problem. But you could sail right through the middle of those and not realize you're there unless you're looking under the water. Because a high concentration of trash might be 1,000 pieces per square mile instead of 10. But 1,000 pieces per square mile is actually not visible from the surface as a contiguous mat of garbage. Those are actually not really common. Anyway, those gyres, imagine that you're on a sailboat right there. I gotta give that guy a boat. Okay, imagine you're on a sailboat right there. Which way is his sailboat going to sail? West, right? Because you've got, please look at me, please look at me. Both of these wheels are going to push his sailboat that way. Y'all see that? This is important. Do we all agree that the winds are going to push that sailboat west? Visualize, if you will. I slice the planet like a grapefruit. I want to slice the planet like a grapefruit, and I want to look at it sideways. That's what I've drawn over here. You'll need this drawing. This is Indonesia, Ecuador. I slice the planet like a grapefruit. Slice it at the equator, look at it sideways. Can't wait? Coal Senator Grant.
Gotcha.
I'll give you 3 minutes to get that drawing. Hurry up.
They're two different drawings, right?
We have normal conditions La Nina on top and the unusual rare El Nino at the bottom. If you can't tell, please look up. I've got Indonesia, the surface of the equator, and Ecuador. Here's the ocean, here's the sea bottom, this is the sky. The South Pole would be like right over here. Center of the Earth is right on the board. The North Pole is a couple of feet into Miss Davies' room.
Are those clouds?
That's one cloud, that's another cloud. I can give you a couple minutes to write this, but please hurry with that.
Wait, you flipped it like this?
Yeah, I can give you a visual. This is the Earth. We slice it at the equator. You're going to look at it sideways. So here's Indonesia, here's Ecuador. See? Cut it at the equator, look at it sideways.
Wouldn't that be like the core?
So this is the core of the Earth. That's right, like a grapefruit. Does anybody here follow international soccer?
Yeah.
I heard Barcelona-Chelsea was all time today.
Really? What happened?
I don't know, my homie's just telling me about it right now.
Chelsea?
I think you know that I'm Argentinian, right?
Yeah.
So all of my homies tell me every time Messi has a good game. I just got 6 emails and 2 texts about it.
You remember when Germany beat Argentina?
I don't want.
Where's Germany lost?
Why do you want to talk about that, bro?
Oh, right.
Love
you,
right.
David.
7?
That's like Argentina's Pearl Harbor, kind of. I do remember that day, dude. That was like, yeah, that was pretty bad. I really wanted to kick something. Like, that guy earned it. That was honest to goodness, just a glorious goal. I was just looking for like, come on, infraction, somebody fouled someone, come on, something. And that was an honest, good goal. What?
Someone made a cake where the top of it was like decorated to look like the Argentinian flag, but when you cut it open, it was black, red, and yellow.
Is there a memorial?
I'm not a nationalist. I can take this. That just happened to be my children's introduction to world soccer. And we were in the Sierra, because it happens during summer, you know? So we drove from 9,000 feet for basically all of like the World Cup that involved Argentina. And my children were following it, and I was like, you see guys, this is your heritage. Like this is why my country people are so crazy about soccer. We're pretty good at it.
Not good enough. Not good enough.
For the final, we took over like half of a big restaurant with all my homies from the Sierra, and everybody was like rallying, and we were all like glued to the screen. And for those of you who don't know, the most recent World Cup, Germany beat Argentina at like 90 seconds left to go, 30 seconds left to go. This like scrawny guy that had never played in the World Cup had been on the field for like a minute and a half. And he made like a laser attack on goal that was just majestic.
And Messi had a chance to tie it up with a free kick and completely blew it.
Yeah, I mean, that happens. You gotta forgive him that. You know, nobody can carry a whole team, but Germany really earned that one.
We won this time.
All right. I'm glad everybody's had time to draw while we were talking about soccer. Please look up. I can just get to the bell. This is an interesting topic. Climate's complicated, and there's all these wacky things on our planet that move energy around. I showed you the biggest one with that current, the conveyor belt, the thermohaline current, but there's a lot of big, complicated climate details. El Niño's one of them. Every 4 to 7 years, the Pacific Ocean goes from normal to abnormal. And a lot of people are stressed how this cycle will respond when we have climate change. Normally, here's what happens. Please look up. That westerly wind pushes the Pacific Ocean surface water toward Indonesia. So all the hot surface water piles up, and you get steamy, hot and wet conditions over Indonesia. That forces cool upwelling off the coast of Ecuador, and a cool convection current of dry, cool air falling. This is normal. And it's one of those weird things about our planet. If you think about it, Indonesia has the same latitude as Ecuador. If you go surf in Indonesia, the water's so hot it's kind of unpleasant. A couple of my friends spent like 12 days surfing there this summer and said that after a full day of surfing, it's kind of gross because you've been in like a warm bathtub all day. People wear white t-shirts to keep from cooking in the sun. And every now and then, you just go for a dunk and then fan out the shirt so that any air movement gives you a little bit of cooling, because otherwise it's just unpleasantly hot in the ocean in Indonesia.
What is the temp there?
Like mid-80s. Like it's kind of like a tepid bathtub. It's like you're in somebody else's pee water. It's not fun. But, yeah, I said it. But if you go to Ecuador, because of that upwelling, like you got to wear a 7mm wetsuit if you go dive the Galapagos Islands. That's really, really cold. You know, this is some of the wettest rainforest on the planet. Ecuador is mostly covered in deserts. This is kind of a surprising difference given that they have the same latitude, unless you realize that the normal movement of material transfers heat over there and generates cold over here. Like this, please look up. You take all the heat and you push it that way. That draws cold water up from the ocean and creates a back eddy of cold falling air. Ecuador has really strange climate for being on the equator. But every now and then, for reasons that are not well understood, that wind stops. I can give you another detail for the science nerds. Should I bother? How many of you want more information than wind stops? It's not just wind stops. It's actually that these gyres shrink and pull away from the equator, so they no longer push that water. Okay? Now, when that wind stops at the equator, please look up. You're not stacking up all the water on Indo. It just stalls in the middle of the Pacific. So you have spread out, dissipated steam and rain, which means it's drier and cooler on the Indonesia side, but wetter and hotter on the America side. Be right there. Like that. Ashley?
Never mind.
Fine. See? There's that hot water piled up against Ecuador. And if you look where it says El Nino and there's that little squiggle above the end, look at how much warmer it is everywhere up to California compared to La Nina conditions.
Wait, where is that?
Where's what?
Map.
I can help you.
No. I mean,
That's Australia, South America.
Oh my god, what the
black
hell?
is the.
Hey-o! Alright. Now everybody got it? Okay, back to me. Back to me. Back to me. You can see that usually there's a bunch of cold. But when all this hot water stays on this side, it just kind of like stays close to shore. Instead of all that getting pushed across the equator over here, look at how much rainfall and heat there normally is. During an El Nino, that doesn't travel. Those wheels get really small and weak. So instead of pushing all the heat over to Indo, during an El Nino, we keep the heat, and thus we keep the evaporation. You may know that in Santa Barbara, El Ninos usually mean a warm ocean. So I was catching yellowtail at the 1 mile and 4 mile reef right outside the harbor. And you might know that we usually get extra rainfall in Santa Barbara El Ninos because we have all the water vapor here. Coincidentally, the last El Nino was a teaser. It got really hot in the ocean, but we did not get more rain. That was a fluke for us. Preston, do you have a question?
No.
You go?
Why does the stop?
I don't know. And I don't think anybody knows. So there's an interface with another cycle that seems to have a rhythm, but it's not clear if there's causation or correlation. It's called the PDO, the Pacific Decadal Oscillation, but nobody can really explain it to me.
So like the AP test, they're just gonna ask you like.
I believe so. I don't think the AP test would ask you that question. They would never ask you why it stops. Yeah?
So El Nino is basically just when there's warmer water, it causes more.
Yeah, so I can try to say something. This might be helpful to everyone. Hold on. What makes the El Nino is that glob of red, the warmer water and evaporation here in Ecuador. Josie, that usually affects all of the Americas, but that gets more complicated. So you can have an El Nino in Ecuador, that's definitely El Nino, and that wouldn't reach Santa Barbara. Having impacts all up and down the Americas, that's a whole bunch of dominoes down the line. But what makes El Nino is the equator. What happens at the equator between Ecuador and Indonesia. That's the El Nino. Who else?
Is it predictable? No.
Not really. Like, you can tell that weather's coming for us as the dominoes start to fall. So people say, oh, we've measured Ecuador's water temperature, there might be an El Nino. And then they say, oh, we've got more water vapor spinning around in the gyre, we might get an El Nino. And then they say, oh, the Alaskan jet stream is superloading with warm tropical air, we're probably going to get an El Nino. And then it hits us, and then we can call it El Nino. So for us, it's only predictable when triggered by Ecuador. Ecuador can't predict it until it starts to happen. Anybody else? Hey, we made it. Will you please click stop streaming for me?